Welcome to our podcast. Today, we're diving deep into the fascinating world of programming languages and compilers, specifically the journey of compiling C code into a unique representation known as flipjump. Now imagine for a moment that you're trying to speak a completely different language, like trying to communicate in ancient Greek after growing up in modern America. That's a bit like what a compiler does. It transforms one language, C code in our case, into another format that's understandable by a different system, like RISC-V architecture. In our discussion today, we're specifically looking at the c2fj compiler, a tool that proves a remarkable point. Any program can be reduced to a series of simple operations, or as they call it, not operations. It's a remarkable feat of engineering that shows just how adaptable programming can be. You might be wondering, what's the significance of converting C to flipjump? Well, it's not just a matter of making something visually different. This conversion process optimizes code execution and enhances performance on specified architectures. Think of it like a chef refining a recipe for efficiency without losing the original flavors. Let's break down a key player here, flipjump. It's not merely a whimsical name. It lends itself to a whole architecture that's designed for optimized performance with minimal constraints on size. That means larger C code bases can be compiled without a hitch. This is particularly interesting for developers who often grapple with performance and efficiency in their work. Here's a simple example to illustrate. Take a C program that calculates prime numbers. Not only does it get transformed into RISC-V, but then it goes even further to become a flipjump file. Imagine watching a recipe transform layer by layer, first the ingredients, then the prepped components, and finally, the beautifully plated dish. In the world of programming, we see C turning into ELF, executable and linkable format, then into FJ files, the flipjump representation, culminating in a .fjm file that actually runs. Speaking of running, did you know that the c2fj compiler supports a variety of options that really customize how the C code is compiled? Think of it like setting preferences when ordering your coffee. Do you want to define breakpoints, step through the operations one at a time, or even unify everything into a single file? It's like having control over how your dish is prepared. But how does it really work behind the scenes? Well, it's wonderfully complex. Essentially, it breaks down syscalls, functions that request a service from the operating system, into a bad RISC-V op, which then gets parsed into what flipjump understands. Imagine a translator working furiously to make sure the essence of a conversation is captured in a new language while also ensuring it sounds natural. Now, if you're intrigued by how memory and jump tables play into this process, here's a thought. Every time a program needs to execute a command, it relies on pieces of memory that can be read and written at will. This means that within the flipjump context, developers have incredible freedom. They can essentially rewrite their own rules in how operations are conducted. I find it exciting that this whole system seamlessly integrates testing as well. Just run PyTest, and bam, you're assured that everything is functioning as it should be. It's crucial, especially for projects that can scale. And let's be honest, running tests feels like getting the green light before a big event. As we wrap up, let's reflect on the impressive journey of c2fj. From compiling C to RISC-V and then to flipjump, it highlights the beauty of transformation in technology and programming. Next time you write that piece of code, think about the incredible journey it undergoes. So for our listeners, what are your thoughts on the potential of new programming paradigms like flipjump? Do you think we'll see more compilers,